This program is brought to you by Stanford University. Please visit us at stanford.edu.
Does anybody want to kind of summarize, try to do this a little bit more Socratic like Channing does, like what we're actually trying to do?
We're trying to find the answer in Perry's.
Sort of.
Have we done that yet?
So we're trying to see, so what has been going over in the last few lectures is we're trying to see how a drug is going to respond in a body. So we're going to inject a drug, and then we want to see what its concentration is over time. And what we're doing is we're going through a few simple examples of building up models from 1 tank, 2 tanks. We're going to go to like 4 tanks, and then on the exam you're going to have to do 10 tanks. No, just joking. But we're building it up to try to to try to actually, to build up to this, basically your next problem set, not the one that's due Wednesday, but the thing after this fast farm, where somebody actually went and took some data on a human or on a dog or whatever animal they chose to do it on, and then looked at the pharmacokinetics, and then they built a model that they thought actually matched it. So the first half of the class, we'll be going through the next extension to the 1 tank model. We'll be going through the 2 tank model. So I came prepared with the laser pointer, and actually the lights are working okay, so that's good. This is good. And then for the second half of the class, we'll do this basically multi-compartment model, which is a fast farm thing. So it's just an extension of this. And the reason why we're going through this is so that you can you can understand the math in this to kind of guide you in terms of trying to understand the more complex model. Because it's really it's basically the exact same thing. So the problem statement is essentially the same as before, where we have a tank, and we're going to inject some drug. It's going to be leaving at some rate. But now instead of just being in 1 tank, it can be in 2 tanks. So you can think of this in a model in terms of a human as basically being tank 1 being this well-perfused tissue, stuff that gets a lot of blood flow, and the tank 2 being poorly perfused tissue, so things like fat. And then if you were actually going to, then what would happen in real life is you'd take data, where you'd go and measure, you'd inject a drug, you'd go and measure some concentrations, and then you'd go and fit your model to that. So you'd go and see, you'd go and adjust like the size of this tank to kind of match what is actually happening. So there's a bunch of constants here, so I guess the other thing I should mention here, I would encourage you, there's a lot in these kind of this lecture and the previous lecture, and it would encourage you to kind of go through the math. We're going to try to highlight the key points here, but it's a little bit more in depth than what was maybe done earlier on in the class. So he has this kind of fudge term here where you're going to have this m naught, where there's some basically massive drug that's absorbed in compartment 1. You have these flow rates, so it's going out and in, so these have to be matched, but these are variables. Something to keep in mind is the units of rate, so we'll see in a second here why these rates have units of volume per time, but it has to do with basically the way he defines his concentrations, but clearance, so the amount of drug leaving, is going to have this, a rates of units of volume per time, and there's a few other things there that maybe I'll find out was important in a little bit. So hopefully by now you're all becoming very familiar with basically in all these problems we've done, whether you've been doing heat transfer or mass balance or now a non-steady state mass balance, you're writing the same basic equation in the beginning, where you're going to where you're simply going to look at your boxes, your reactors or tanks, and you're simply going to write down the equation. So probably you should all be able to now do this in your sleep, right? Where you can look at that model and you can think, well, we want to see what the change in concentration of tank 1 is with time. So this is the mass balance. We have the derivative of concentration with respect to time times the volume, so that's a mass change in that tank. And then how can that change? So we have 3 ways it can change. You can have mass entering the tank from tank 2. So you can have mass entering tank 1 from tank 2. You can have mass leaving tank 1 going into tank 2. And those are proportional to the concentrations in those tanks. You can have your injection. So you can inject drug into your tank, and then it can leave at some rate that's in a body having to do with what you metabolize, or in this problem set, that can be incorporated in your dialysis machine. So that's the complete where all our mass is going in our system. And then in the compartment 2, same left-hand side. The right-hand side is a little bit simpler because we only have mass entering and leaving due to those 2 pipes. And you don't have the reaction term or the injection term directly. So what we're now going to do is we're going to go through and we're going to think about how we can inject different drugs. It's good to think about what effect that'll have. And then and then we're going to non-dimensionalize it. And then we're going to show you the solution and talk about that. So what ways can you think of getting a drug? Anybody? How do you take your drugs?
Smoking.
I would think smoking would fall under the GI impulse. So this would be something. Well, no, actually, I take that back. That's like this. That's like an injection, right? Well, it depends, I guess, how long you smoke for. How do you take? So you get an injection of a drug, right? So that's a simple way to do it, where you're basically going to go to the hospital. Somebody's going to have a syringe, fill it up with whatever your drug of choice is, stick it into you, and all of a sudden you're going to have a very high concentration, and then that's going to leave your system after that. And you're not going to be getting, at times after that injection, you're not going to have more drug entering the system. So we can mathematically represent that as a delta function. If you go to a hospital, you can get an infusion, or you can just get an IV stuck in. So somebody will put an IV in you, and basically at time 0, they'll start pumping in at a certain rate, and they'll just keep that constant over a certain rate. So that's a very good way to maintain a specific level of drug in your system, but it's kind of difficult to walk around with an IV in your arm. And then the other way is probably this impulse, where you can think of what happens to the concentration of drug in you if you take a pill, right? So if you take a pill, you pop it in your mouth, it's going to go into your stomach. Initially, it's going to have a lot of surface area. So presumably, the amount of drug you get is going to be proportional to how much surface area you have. And as that decreases, as your surface area decreases, you get less and less drug. So you have kind of a maximum. You have a rate at which you're getting the drug that decreases with time. And he's just going to call this exponential and you could imagine that there's other functions that are going to govern this.
Why is it modeled as a step?
For the infusion rate? So this is for the just having an IV in. So presumably if you have an IV, somebody sticks an IV in, they're going to stick at some point you're going to turn on the IV and it's just going to be dripping in at a constant rate. So until your IV runs out. Or they turn it off, whatever.
No free drugs.
What's the question? So he has these constants in front. So R naught is, let me remember what these are. That's, what's that?
The infusion rate, it says it below it.
Right, the infusion rate. And then M naught is this amount that's absorbed.
So what's actually graphed is GT9. It's just a CT.
Yeah.
It's just the unit step scaled by whatever R.
Yeah, all that will come in when you go and actually solve the equation. It's just the first simple model. So K0, he gives the units of the K0 conveniently on the other page, so we'll just skip that. So if you continue with the chemical engineering class or other engineering classes, you'll probably get familiar with non-dimensionalizing equations. So Channing went over that last time, and we're going to do that, go over that again for this example, just to make you more familiar with it, and also to kind of think through what its implications are in the problem, because we're going to go over the solution of this, or a solution to this, that is a non-dimensional solution. So kind of the key to non-dimensionalizing a problem is to take your dependent and independent variables and divide them through by constants. So, or normalize them by constants. And the key to picking those constants, they only really have to satisfy two things. The constants have to have the same units of the thing you're trying to non-dimensionalize. So if you're trying to non-dimensionalize time, you better divide it by something that has the dimensions of time. And they have to be constants. So don't pick something that's going to change with time, or else that's no good. So just to set out and start this problem, we don't maybe a priori know what constants we want to combine together to non-dimensionalize concentration. So we're just going to call it C star in absence of having something better to do. And we're going to do the same with T, where we're going to come up with a non-dimensionalist time tau, and we're just going to divide it by T star, so time by T star. And then what you do is, if you go through the algebra here, so basically what he does is he goes and plugs in. So every place you have t previously, so dt, this was dt before he non-dimensionalized it, so he just stuck in tau. So replace t with basically tau times t. Tau stays in the derivative. T star comes out. It's a constant. And then you go through that for each of your concentrations. And I guess there's a little typo here. And at least we then non-dimensionalized part of this equation when you go through by just plugging in our non-dimensional concentrations. And then you got to think a little bit about, or at least the way he sets up this problem, you got to think a little bit about, now we want to decide what T star is going to be. And you could have, so he gives some choices for T star. So these all have the concentration, the units of time. So V is just a volume. And if you remember, K has units of volume per time. So that's kind of units of time. You could have V2 divided by Q. But being that it turns out that you kind of get the nicest solution to this equation if you use this non-dimensional time, where you combine the two volumes and divide by the clearance rate. And this is one of those situations where, like, you could pick these and they'd be fine, it'd be okay, but if you kind of know the solution, if you know the answer to the problem, you can, it makes solving it easier. So you'll come across that in the future. But what's that?
How would you figure that out?
Basically, people have been solving these types of equations for 200 years or something like that. So for the Q up here, you didn't use it. He just decided to non-dimensionalize time in this way. So these were choices.
It's kind of arbitrary as long as it has the same units.
Yeah.
Even the things are constant.
In terms of, like, if you were asked to have something on an exam, like, you don't have to come up with the one that's going to give you the prettiest answer. As long as it has the right units and is a constant, it's okay. But he chose to solve it this way. And then he did something which you often do when you start having lots of constants in long equations. You just define new constants. So V1 divided by V2 comes up a lot. Q divided by K comes up a lot. So you just define them being alpha and lambda. And then you plug them in, and you start getting something that's a little bit simpler. So we've non-dimensionalized these parts, and now we want to look at our injection function. So what he does first, I guess just to write nicer equations down, so he just defines this, another trick just to make things look nicer, you just define it as being this big G of t. And now you have this set of couple differential equations, which the first thing we're going to go over is we're going to look over, well, I said we were going to go and look at impulses, but I guess the first thing he does here is looks at just as a check that we've done things correctly, you're going to look at the steady state solution to these things. So he's going to do one of my most favorite mathematical moves, where you're going to come up with a steady state solution. So you're going to basically make these two sides equal to 0, and you're going to make sure that your answer sort of makes sense. So when you do that, he basically writes down the answer, but hopefully by inspection you can kind of see that when you set this equal to 0, y1 equals y2, so the concentration at steady state, the concentration in both tanks have to be equal, which hopefully makes intuitive sense to you, that if you're flowing this in at a constant, you could imagine if you put in a drug and you put in an impulse at a certain time, short time after that, there's going to be a different concentration in the two tanks. But if you then keep on flowing fresh water through there for a very long period of time, the concentration in the two tanks is going to be equal. So that's just what that's saying. And then if you go and look at the top equation, so we saw that term 0, so you can see that basically the concentration in the tanks, in either tank, which is the same, is just going to be the concentration of your impulse function at long time. So if your injection function at long times has 0 drug coming in, at long times you're going to have basically no drug in your tanks. If you have the step function, or you have an IV at long times, you're still going to get drugs. You're still going to have drug coming into the system, and then there's going to be an equilibrium concentration that results in that. So now basically what he does is he goes through the non-dimensionalizing each of these, the impulse, the step, and the GI impulse. And it's basically the same thing that was before, but you'll see that kind of the value you choose for this C star, this non-dimensional concentration, changes depending on your function. And that just comes out to, and that's just a function of trying to have a nice solution at the end. You'll see that all of these have the right concentration, but in the impulse you get a C star of m naught over v1 plus v2, whereas here you get it r over k, and here you get the same thing back. And what he did to non-dimensionalize this is the same thing that I described before. So hopefully you're getting a feel of how to do that. It's mainly just algebra. So the equations that we basically had almost on right initially after we went and looked and wrote down the the mass balances for the two tanks are basically a set of coupled ordinary differential equations, and then we spent 2 pages of math non-dimensionalizing them so that when you solved it, you get a pretty solution that's a non-dimensional solution and lets you see a little bit more about how these sets of equations behave. So what is basically plotted here, a fairly easy to read setup. So we have the concentration in tank 1, the concentration in tank 2. We have this non-dimensional time. And then we have how this is changing as a function of lambda. And this is solved, for an alpha of 0.3. So a situation where you have a pretty big tank 2. So your tissue, if you think about this as a human, there's a fairly large volume of the poorly perfused tissue versus the well-perfused tissue. So you get a lot of information about the behavior of these two equations by simply looking at the extreme cases of lambda. So what you can see, so what's the situation where basically lambda is infinity? So what does that correspond to, like when you think about what's actually happening? Anybody? It's okay. So we have this very large flow rate.
And things kept in the body really clear. It's not metallized or extruded that fast.
So basically, it's almost like you have one tank. That's what I would say. So you have a situation, and if you look what's happening in this plot, so the case where lambda equals infinity, these two curves are the same. So that's the limit.
Why would it be like one?
So it's basically you have this you basically circulate, you could think you have two tanks and you're just pumping water, or so whatever you're pumping, back and forth between the two tanks very quickly. So when you inject something in, before it can get out, it's had a time to equilibrate between the two tanks.
Doesn't it just make the clearance rate is really small?
Well, it's the ratio of these two, right? So you could think of it as a few ways. Like one situation would be, yes. So it could be this. You could have a very slow clearance. So is that what you said? Sorry. Okay.
Versus the flow into it. But
Yeah.
I don't see the difference between one and two.
Well, it depends. So you're right. It could be two things. You could have it's the ratio, right? So you could think of how the ratio will become big or small, right? So it could become big because you have a very large numerator. It could become small because you have a small denominator, that type of thing. Conversely, you could think of the situation where lambda is equal to 0. And what you have is basically, this would be the situation where very little material ever gets to the second tank. So when you inject material, it is, even at long times, very little, or in the limit of lambda equal to 0, none of it gets to the lower tank. The other thing you see from this graph is you see basically how this behaves as a function of lambda. So what's the important range? And basically what you see here is basically 5 is equivalent to infinity. So once you get to a ratio of 5, or a little bit more, there's not much difference. So that's sort of the useful range.
Wait, one of them is one tank and one of them is
Yeah. So the bottom graph is the lower tank, Y2, and the top one is Y1.
Oh, now I get it. That makes sense.
So now that we've got the two-tank model under our belts, we can use that to get to something, I guess, maybe you consider more interesting, I don't know. You have a homework assignment on it, so maybe you'll pay attention more. So back in the day, some chemical engineer, somebody who took E20, probably from Channing, even though, 'cause he's been around forever, decided that they were going to go and get some data. They were going to go and measure what happens in a dog or a human. I guess we have a human. When you go and actually inject a drug into them and see how it clears. And they probably tried the one-tank model, and they said, oh, this doesn't really work. The things I measure in different tissues, it doesn't really match. They maybe tried the two-tank, didn't work. They tried some other things. And what they came up with is this model. And what this model is, we'll go through it. But this is basically using the principles that we showed in the one and two-tank models, but it actually fits. So this has a level of complexity in it that actually describes the human at some level that somebody was happy with to publish a paper on it. So, but they're using the exact same principles that we went over before, where they thought of this as being different tanks with different flow rates and different behavior, and then the behavior in each tank is kind of dependent on what you're trying to model. So before we had two tanks, and we said that one was highly perfused tissue and a poorly perfused tissue, and now we just have this 4 tanks, which is just basically dividing things up a little bit, I guess, in a way that looks a little bit more like a human, and therefore it will let you, I presumably model what's actually happening in a real person. So the basic idea for the human or the person is that you're going to have a blood pool. And these are real numbers. Channing wanted me to emphasize these are real numbers. Somebody actually went and measured these. So they're real, declared. Probably valid for everybody in this room. No. And then you have different types of tissue. So he's calling this viscera. So this is the well-perfused tissue. So adrenals, thyroids, your brain, for some of you, I guess, heart. Lean tissue, so your muscles, something that's poorly perfused. And then basically something that's even poorly perfused, which is adipose tissue. So basically fatty tissue or bone marrow, etc. And we're interested in, so I should mention, I put up, so this is the basis for the Fast Farm project that is going to be due, it's going to be due like the Wednesday after the exam next week. So like normal, but there's going to be a prom session for that on Wednesday, and I encourage you to do it. So the guy that runs this homework, sorry, this could have been on the side here. The guy that, there's a guy named Taku that was an undergraduate here and stayed on and is in the petroleum engineering department. He's getting his graduate degree, but he's been doing this. He just loved E20 so much and this project so much, he's been TAing this part of it for like 7 years or something like that. So he'll go over the details of how to actually do the homework assignment. And what it basically is it's going to be, there's some MATLAB code. Don't worry if you don't know MATLAB, they'll tell you what you need to know. But he'll kind of show you a little bit of the operations of how to run this little program that's basically going to solve the equations that we're setting up in class here today. So that is actually posted on coursework, and you are encouraged to download that over the weekend. And there's a little instruction manual that spend 15 minutes reading it over. Just after class on Monday. Yeah, just like normal. And the point of that is, and basically what the model we're trying to set up is something where you have a human, and then you're trying to inject a drug and clearance. So the clearance is going to be a dialysis machine, basically. So, yeah, sorry for not announcing that kind of at the beginning. So got the injection like before, and then clearance. And what will become apparent here, so the way this sort of differs from, the way this is a little bit more complicated than the two models we set up earlier is what actually happens in these compartments. So you notice that there's a box with two lines in it. And basically the way this is broken up is there's kind of two pools within a compartment. So you can think of adipose tissues being basically a bunch of solids and a bunch of liquids. That's what they're basically saying here. Sorry, there's two things actually. You can say that within a certain box there's tissue and blood, and then within those we're going to have to talk about if there's something in liquid and solid, basically something that's in water or something that's everything else, so proteins, fats, lipids, and the behavior of those are going to be a little bit different. So that'll become hopefully apparent here in a second. When we go and think of doing the actual mass balance on one of these. So hopefully this looks familiar, but we have a few more definitions here than before, and simply just a concentration for each tank. So within each tank, we need to think of that there's this water fraction, there's a water fraction, so how much of, when you think of a tissue, how much of it is water and how much of it is everything else. And then you need to think of the concentration of the drug. Where can the drug be? So the drug can either be in a bound concentration, so that's the everything other than water fraction, or it can be in the free concentration, or it can be free. So it can be in the pool that is just water. And then we're going to we're just going to write down mass balances, with that being our model. So it's the same thing as before, but with it can be in a few more places in each tank. And so rate of accumulation in the blood tank, in basically the blood pool, the one on the top. So this is the free concentration, the accumulation of that. And that is, you'll see here, proportional to the amount of liquid there is, or the water fraction in the blood. And then the bound fraction is proportional to the amount that's not in the water, so 1 minus that. And then where can this drug go in the blood fraction? So it's the best to QB, right? So the first term is basically, we're going to look at the first term of where it's going to leave. So we're in this tank, we're looking at this tank, and then we're going to think, okay, it can leave here in QB. Given flow rate, and then you're doing basically the same thing where you're having to break it up, and it's either in the free concentration or it's in the bound concentration. And then you can think of where it's entering. So the next thing is where it's entering, and what we have is the viscera, the lean, and the adipose tissue. So basically what those next 4 lines are looking at is the amount of drug that's entering this blood pool from these different tanks. So they basically just, all these tanks basically add up and go in to that. And it's the same thing, it's the same type of mass balance as basically up here, but you're doing it with the subscripts for each of those individual tanks. So that takes us down to the 4th line, 5th line. Basically what this is it's a place our drug is leaving the system. This is our dialysis machine. So it's only basically leaving due to our dialysis machine, and it's proportional to the same things that and it's the rate that it's leaving is just proportional to the same free and bound concentration that we were talking about earlier. And then we have to have the drug added. So this is our impulse. And you can think of it being the injection or taking a pill or all sorts of things like that. So I'm not going to go through all of these other ones because that would be kind of lengthy. And it's basically the same thing. I think it's sufficient to say that there's one little difference between these. When you go and look at the viscera, so if you follow through this weekend, or whenever you choose to look at the fat and the adipose, you'll see that they all have the same form as the viscera up until this last term here. And basically what they do is they add on a term at the end, who was originally creating this model, that basically it's a clearance term that says there's a rate at which this drug is leaving the viscera due to, I mean, you don't know what it's due to, but presumably it's due to it's being metabolized, or there's some other mechanism for it to leave other than your dialysis machine. So I guess in order to fit their model well, they had to take this into account, that there's this rate that the drug is leaving. So now we have, instead of 2 equations like the 2-tank model, we now have 4 equations. And they're sort of nasty, I guess. They're not non-dimensionalized, but we're not going to deal with that at the moment. So now we can think about basically what's known, how to solve this, and what is going to be the behavior of the solutions to this problem. So step back and think about what are the different things that we just wrote down there. What is their physiological meaning? So we can simplify things down. So these fractions free or bound are really simple. They're constants that are relating to basically how much water there is or how much other stuff there is. And I guess the take-home message is it's almost all water. I guess we're not 98% water, but that's what these values are, so we'll just go with it. But in the adipose tissue, there's significantly less, so it's just fat. So fat's not water, so these are the values. So those are good, those are just constants. These are basically models or values that have to do with how our drug's leaving. So like these, basically a constant is going to have to do with how good our dialysis machine is. We're going to have rates, so basically a rate here. So you'd have to measure that in order to see in the viscera like how your drug is leaving. So these are things you're interested in, or things you're interested in fitting your model. So the more interesting assumptions we're going to have to make is we're going to assume a few of the bound fractions, or the solid, sorry, not the solid fractions are the same, and that'll become apparent in the next slide. And we're going to assume a little bit of equilibrium. So in terms of equilibrium, what we're going to basically assume is that if you look in one of these tanks, or one of these tissues, you're going to assume that, so the two things that you're going to see in the next slide is you're going to say that the amount that's in the solid fraction is the same for the concentration of drug bound in the solid fraction for the tissue or the blood is the same. This is an assumption of the model. And you're going to assume that there's an equilibrium between the amount that's in the blood and the amount that's in the amount that's in the solid fraction and the amount that's in the free fraction. So once again, these aren't, say, fundamental things. This is somebody kind of sitting around at their computer, or pencil and paper, having measured something, and then trying to think about what's actually going on and what assumptions are good to make and what aren't. So so what is shown here is basically a statement of what I just said. So where they show this basically equilibrium relationship where you have the concentration of the solid in the solids of the adipose bound is proportional to the amount in the free of the amount of the drug in the free fraction of the adipose by this equation, which they give you the constants for. And this is kind of this type of relationship is when you go and measure how things bind, it's sort of a Langmuir binding relationship. So it comes up in the future. It's a kind of a common relationship that comes up when you look at binding and you're trying to fit it to a model. And then this is the statement where you have the amount solid in the liquid and bound fractions being the same. And at least in the adipose tissue, they have it. They don't make that same assumptions, but they have it, and they have a linear relationship where they have it, where the amount in the tissue, or the solid tissue, is proportional to linearly to the amount free. And then they give this proportionality constant. Then somebody at some point measured a rate of reaction, and this is like a Michaelis-Menten type reaction rate. And then they come up with this dosing strategy. So you now have 4 differential equations, a number of assumptions, and then somebody was very nice and basically plugged this into MATLAB, and you're going to now, for the fast farm, you're going to basically look at the behavior of this equation. And the next number of slides in your handout or in your course reader show some of the behavior. And we can quickly go over at least a little bit of that in the last few minutes. So, I mean, basically what is plotted here is the behavior of kind of individual parts of the equations, not the equations, but of the equilibrium relationship. So this isn't a solution to the coupled differential equation. This isn't a time-dependent process, but simply here, like if you look back a slide, you'll see that there's an equation relating the free concentration to the bound concentration, and it's just linear, and it's related to a slope that was given. This is just the rate of reaction, so that's that Michaelis curve that we're talking about. And then you can see that the amount in the bound fraction has some relationship to the free concentration, that at low concentrations it's nonlinear. And at high concentrations, whoa. I guess they tell you not to pace, right? I'm not telling you how to do this. Sorry if I'm pacing too much. And at high concentrations, it becomes linear. I'm not sure there's time to go over any. So basically, if you should look ahead, and you should. So So there's about 5 more pages where what they're going to do is go through the different cases. So they're going to look at a different drug, and those different drugs are going to have different values for like different equilibrium relationships between the bound and free, and that's going to relate to at a microscopic level. That is going to relate to the properties of the drug, whether it's like more hydrophobic drug or not, or how just the body actually metabolizes it. And then there's going to be a basic solution to when you actually go and solve those differential equations with at least one value of, at least for a situation where they turned on the dialysis machine at, I forget what the rate is, but they show that you turn on the dialysis machine and you basically have a quicker drop off of the drug, which makes sense because you're turning it on, you're increasing the clearance rate of the drug, and you can see the behavior of that. So what the fast pharma assignment's going to do is you're going to just play with the behavior of these equations to see what is the optimum. See how turning on a dialysis machine or how increasing the dialysis at different times is going to lead to the most rapid clearance of the drug within constraints, I guess real world constraints or constraints of the problem statement.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.